but if for anyone who doesn't really like to do computer programming and doing the stuff that we talk about in this class and other programming classes, the pay may be good, but it would be pure torture if it's really just for the pay. I mean, if you like it already, and the pay is like fringe benefit, right? It's like, oh, cool. I didn't know that I can have fun and get paid at the same time. But picking computer science, just because of the pay, is not going to be. It's not going to be fun.
Well, when I first got into computer science, I did it because I wanted to make video games. But if you look at video games, all the artists don't get paid jack, but
really
programmers get paid a lot more. So that's why.
I was under the impression that they have enough people doing the programming and just not enough people working on the art or the story arcs, and stuff like that.
Artists are a dime a dozen is the problem. Everyone can be an artist, not everyone can
Really?
Yeah, I liked it for the problem solving. I was in the military, so we had a lot of data to sort through. And so the first program I was actually sorting through all of that, and it was just so much easier to do my job. So I like it for that.
Okay. I'm gonna, just for the career GPS, thing, I'm gonna include IBM's Programmer's Aptitude Test. They have been doing that for years. They have it's more like an IQ test. If you have taken any type of IQ test, it's mostly just about solving problems. So IBM has their own, what they call the Programmer's Aptitude Test, which is basically just a longer version with more number-related problems. And that test, basically is for IBM to kind of filter through people and find out who is suitable to get into programming and the more technical side of stuff, and who might be more interested in, let's say, marketing or the other side of IBM. So I might include that too also. If you search on the internet, you'll probably be able to find those questionnaires, and it might be fun to do it. All right, so as promised, what I'll do today is to show you a little bit more about LogicSim. It's not documented yet, because I did not have time to document everything yet. This is a tool that is new to me. I did not originally plan to use it as much as I'm doing it now. But for the purpose of this class, I think it is very appropriate to basically spend a little bit more time on LogicSim to show you what is inside the processor. Because when we talk about the processor and you understand what is inside the processor, by the time we get to the instructions, hopefully you will make a connection and say, oh, okay, so this is the instruction, it looks like this. So behind the scenes, this is what the processor has to do in order to add two numbers, in order to store something, in order to access memory, and so on. So this is what I'm going to do, is to start up LogicSim again, and this time I'm going to work on a slightly different item inside the processor. It's called the ALU, or the arithmetic logic unit inside the processor. This is where things really happen, like adding, subtracting, deciding what to do, and stuff like that. So I'll start with the design of an ALU today. It's not an assignment, for you. Okay, so at least not yet. Okay, so I might give you a homework assignment based on this. I'll give you a file to start with, and then you have to modify it to add features to it. But not right now. Just kind of take a look at what I'm doing here. LogicSim already has components called adders, subtractors, multipliers, dividers, and so on. And most of these, if not all, they have a very similar structure: 2 inputs, 1 output. Okay. Many of these also have an input carry, or carry in, and a carry out. Kind of like the adder that we have constructed, except it just appears as one block here. And you can just specify the number of data bits. So 8 is good. We're going to design an 8-bit ALU, and I'll also use a subtractor here. So the ALU, or the arithmetic logic unit, its only job is to perform calculations, arithmetic operations. Multiplication and division, particularly division, may or may not be inside the processor. All of the earlier day, 8-bit processors like the 8086, well, I think the 86 had a multiplier, but some of the more primitive ones do not have a multiplier. In other words, the processor itself does not have the circuitry to perform multiplication, integer multiplication. In order to do multiplication, you will have to make your own logic to do it. Okay? So what I'll do is I'm going to drag these two units here, and then we'll look at the ports or the pins of these units individually. The top pin is called carry in. In other words, it is a carry going into the adder. It is basically the carry to the least significant bit of whatever we're adding. With the adder that you guys created, or the subtractor you guys turn in for homework assignment, the borrow bit coming in is hardwired to a 0. Okay, but in this case, it can come in from the outside as either a 1 or a 0. The ALU does not decide what it should be. The instructions do. Okay. Same thing with the subtractor. With the subtractor, it is a borrow in instead of a carry in. So these two typically will come from the same source. We call that just the carry in, even for a subtractor. So for the wiring diagram, I'm going to put a pin here, and it is going to be an input pin, 1 bit, no 3-state, and we'll just call that our carry in bit, and I'll make it face south, just so that it looks better this way. And I'll make the connection here, and also make another connection over here. Okay, that's the easy part. I'm moving it so that I get more space to put other items. Go. All right. So this particular port here is one of the numbers to add, and then this is the other number to add. This is the number that we are subtracting. This is the number from which to subtract, and this is the number to subtract from the other one. Okay. So that means we have to have data coming into the ALU. In fact, we need two quote-unquote pins or 2 ports for the data or the numbers to be added or to be subtracted coming into the ALU. So for that, I'm going to go to the pin again and make one first. But when I make this one, I'm going to change the data bits to 8 bits. Okay. And we'll change the name to data in 0 because it is only one of the 2 input ports into the ALU. So I'm moving this a little bit over here so that we have enough room for the D in 0. The other one, I'm just making a duplicate of this one, but the other one I'm going to rename it to D in 1 because there are 2 of them. And for both of them, I will make it face south, so the connection port here is to the south. Same thing here. Okay. There we go. And data in 0 would go into the input, the first input of the adder, and it will also go into the input of the subtractor. This is the number being subtracted from, and this is the number. This is the other number for adding, but it also serves as the other number, or the number that we are the value that we are subtracting from the first one. Okay. So right now, we have a circuitry to bring in 2 8-bit numbers and a carry in from outside. And both of these circuitry, the adder and the subtractor, will perform the calculation simultaneously. In other words, the adder will give you the sum, and then the subtractor will give you the difference at the same time. But as the output of the ALU, you only have one single output. So now you have to kind of pick, okay, do I want it, I'm performing both operations, but which one should be the output? Okay? Well, you need to select which one is the output. So what we will do now, okay, I'm going to move this one up a little bit just so that it aligns with everything else. So with the 2 outputs and with the 2 calculation units, components, the adder and the subtractor, we have to combine it into one single output. So this job is done by what we call a multiplexer. So you go to plexers here, and it gives you all the ways of combining things and fanning out stuff. So in this case, we need what we call a multiplexer. And a multiplexer looks like this, in the picture. It looks like kind of like a funnel. A demultiplexer looks just like this, except it works the other way around. Okay, one input, one input, multiple output. This one has multiple input and only one single output. It combines the output from multiple sources and just pick one as the one single output. It's kind of like a traffic director, only let one car through an intersection. Okay. Now, when you look at the properties of a multiplexer, other than the direction, it also has selection bits. In other words, in order to figure out which one of the input becomes the actual output, you can specify one bit to specify one of two possible inputs. You can specify two select bits to specify one of four possible inputs. You can specify 3 bits to choose one of 8 possible inputs. Okay? So right now, I only need 1 bit because I only have an adder and a subtractor. But in the future, if I have like bit shifting and some of the other operations, I might need to extend the multiplexer. So I'm just building this for the future and say, well, let's go ahead and leave some leeway here. And I'll use 3 possible inputs so this way I can have up to 8 inputs and to merge into one single output, to choose one as my actual output. Are there any questions about what a multiplexer is or what it does? No questions for now. Okay. So if there are no questions, I'm going to draw the connections between these 2 output units here. Okay, so this is the output of the adder goes into the input 0. I'll fix the orange stuff later. So right now I'm just making the connections. There we go. We have an error here, incompatible with, because when you look at the multiplexer, the data bits is only 1. We have to make it the same width as the other ones. Okay. Are there any questions? No. Okay. Now, but this is okay, but that's not everything that we want to do. What about the carry out? In other words, C out, which is the carry output of the adder, and also B out, which is the borrow output of the subtractor. Those should be the output of the ALU as well, because somewhere else in the processor, there's logic that relies on, oh, do we have a carry from the previous addition? Do we have a borrow from the previous subtraction? So those bits need to be output as well, and they need to be combined through the multiplexer. So that means we're not quite done with the multiplexer yet. We want the multiplexer to actually have 9 bits now, and obviously it's complaining because the output of the adder is only 8-bit, and the output of the subtractor is only 8-bit too. So what we'll do is we'll cut off these connections, and what we'll do is we'll use another feature to combine wires into one. So we're gonna remove these. And then what we'll do is we'll go back to wiring and use a splitter, which is also kind of like a combining thing. A splitter is not the same thing as a multiplexer because it's not really choosing. It's really just saying, oh, all of these lines are now bundled into one single cable. Or I'm taking one single cable and separating the individual conductors back into individual logical connections. That's all a splitter does. Okay? So if you look at a splitter, it's really just bundling multiple wires into one, or splitting them into multiple wires again. That's all it's doing. So what we'll do is we'll use 3 splitters in this case. So I'm going to just pop 3 things here, and then we'll work with these 3 in order to do what we need to do here. Let's see, I cannot scroll because I haven't really got to the point where it needs to be scrolled. So if I move this all the way here, then it will start to let me scroll here. Okay, with a splitter, if you click on the splitter, the properties of one, it let you, specify, facing direction. With these 2, I'm gonna change the direction to west. And well, actually, I'm gonna remove the other one because once I work with once I'm done with the first one, I can just duplicate to the second one. It has what we call a fan out, which is basically saying, okay, from one single cable, how many logical units are we creating as the output? 2 is fine, okay? That's not a problem. Bit width is going to be 9, not 8, but 9, because now we actually have 9 logical individual wires that we want to logically group into two groups as the input into the splitter. Okay. And this allows you to specify which individual bit is the top one and which individual bit is the bottom one. So the way I group this is I'm going to group 8 as the top, oops, and 1 as the bottom. So when you look at this number here, I can zoom in like one more level. When you look at these numbers, now it's saying bit 0 to bit 7 is the top one, and then bit 8 all by itself is the bottom one. And now we can actually do a duplicate. So now we have two versions of this. The top one, which is bit 0 to bit 7, is really just the output of the adder and the output of the subtractor. Okay. The bottom one, which is corresponding to bit 8, the other, quote unquote, the other bit, would go to the carry out from the adder on this one, and it will go to the borrow out from the subtractor, like so. Okay. The reason why I need to do this is because I need to do this in order to create a single logical input into the multiplexer. Because the multiplexer is basically saying I can have 8 possible input, and each input has a width of possibly up to 9 bits. In this case, I have to reprogram it to 9 bits. So now that I have this part done, I can go back to the multiplexer and just drag it over here. Maybe a little bit more space. And now I can make one logical connection of the 9 bits out of the splitter into the input of the multiplexer. And I'll do the same thing from the subtractor here. All right. Are there any questions about this step? Why I need a quote-unquote splitter in order to merge 8 plus 1 input into one single logical input, so that I can use the multiplexer.
How will the multiplexer interpret the 2 inputs that you're?
I would need to hook up the selection bits to the outside world also. So something will have to specify, okay, are you adding or are you subtracting? So I'm not quite done with the entire circuit yet, but I'm just making the connections at this point. Okay. All right. I'm leaving some space here because I might, add a, shifter, some other components later into the ALU. All right. So out of the multiplexer, I need to, get the, let's see here, I'm duplicating an 8-bit port here. So the one thing that I need out of the multiplexer is the output of the operation. So I'm going to change this from no input to yes to an input, and the label is going to be the output of my ALU. Okay, if I choose to perform an addition, this output port will become the sum of the addition. If I choose to do a subtraction, this will be the difference of the subtraction. If I choose to do a bitwise shift, this will be the output of the bitwise shift. Okay, it's just the output. And then the other thing I also need to do is to bring out the carry out, because the carry out and also the borrow out is going into the multiplexer. So a part of the output of the multiplexer is also the carry out. So I need an extra pin, for the carry out. So I'll go to pin here and just make an extra pin. Let's say we stash it here, make it face south. It is an output pin. We don't need to specify tri-state, and we'll just call this is the overall carry out of the ALU. All right. So now we run into the same problem as before. If I try to connect the multiplexer directly to D out, it doesn't match, because the multiplexer is a 9-bit multiplexer. Each path coming in has 9 bits, and the output also has 9 bits. The D out is only 8-bit because we're dealing with an 8-bit processor here. So once again, we need a splitter in order to finish this operation. So instead of making this one work, I'll be a little bit lazier and just do a duplicate of this one and flip the direction so it faces east. The one single side faces east, and get rid of this connection. Make the output of the multiplexer connect to the splitter first. So And then the bit 0 to bit 7 would go to the 8-bit output port. And then bit 9, or excuse me, bit 8, which is the one last bit here, would go to the overall carry of the ALU. Any questions about this part of the circuitry? Yes?
So this might be implied, but and you might have mentioned this before, but the output, it knows that the first 8 bits go to the 8-bit channel, and that one remaining bit goes to the
Correct.
single bit?
Yes.
Okay, so it keeps those in line through the multiplexer?
Yes. Yeah. So the multiplexer takes bit 1 of input 0 to bit 0. Okay, I take it back. It takes bit 0 of input 0 to the bit 0 of the output if input 1 is selected.
Okay.
If input 2 is selected, it will bring bit 0 of input 1 to the bit 0 of the output. So it preserves the ordering of the bits.
Right.
Its only job is to say, okay, switch, which one is the actual input connected to the output.
Okay. Thank you.
Oh, that's a good question. Okay, these pins here, this is the selection pin. So if you read the text, it says select identifies which input becomes the output. So this one has a width of, okay, if you look at this one, the select bits has a width of 3 bits. So we need to bring this, also, to the top here, as an interface, or we can bring it to the bottom. Doesn't really matter. It's just a matter of, how you want it to look like. So we'll make it face north, and it has 3 data bits, and the label is going to be operation select. Okay, so I'll just OPSEL is the name of the port here, and we don't need to do a tri-state, so we can turn off 3-state. Say no here, and then just make a connection here. There we go. So now from the outside of the ALU, I can choose 0, 0, 1 to specify a subtraction, or 0, 0, 0 to specify an addition. The other 6 channels are not being used yet. Okay, I'm leaving those for expansion purposes. Okay, are we still doing okay so far with the ALU? We only got 1 pin left. That 1 pin left from the multiplexer is this one here, and it's called enable. When not 0, output is the selected input. Okay, when not 0, output is the selected input, which basically means if it is a 0, then it is not driving the output. It's basically a output enable type of feature. If it is a 0, then the output port is just not being driven, which also means something else can be driving those particular pins, which can be useful depending on how you want to structure your ALU and how it connects to the rest of the system. Yep.
Is that similar to the clock switch?
Yes, similar to that. Yep. So we'll bring this one out, and have somebody else outside of the ALU to actually make that decision. So now we have 1 extra pin. It only needs a width of 1 because we only have 1 single bit here. No tri-state, and then we'll call that operation output enable, and then make that connection. Right, just line them a little. There we go. All right, so now we have a basic ALU, done. So now the question is, what does it do? I mean, we have all these connections here, but what exactly do we want it to do? Well, let's see. Let's see whether we can specify 2 plus 3. Okay, we want to specify the operation of 2 plus 3 and have the output to reflect 5. Okay. All right. So let me go to the input first and specify the input of 2 and the input of 3. So switching back to here. Actually, we want to turn off tri-state, so that way we don't have to deal with the unknown state here. All right, so this is, let's say this is the second number, and we want this to be 3. In binary, 3 is 1, 1. This is the first input. We want it to be reflecting the value of 2, which is 1, 0 in binary. Now, the problem is, both of these are feeding into the adder and the subtractor at the same time. So both the adder and the subtractor are actually performing the operation of adding and subtracting at exactly the same time. The good thing is one is feeding through input 0 of the multiplexer, the other one is feeding through input 1 of the multiplexer. So here, by choosing which one of the input actually gets to become the output, I can now specify, do I want the sum or do I want the difference? They're both calculated at the same time, but I can choose which one becomes the actual output. So here, 0, 0, 0 chooses input 0, which is the sum, but you can see that nothing is coming out yet because output enable is not turned on yet. So once I turn it on, you can see 1, 0, 1, which is 5, and that's my result. Are we doing okay so far with what the ALU does? Okay, it has the potential to do all kinds of calculations, addition, subtraction, bit shifting, and so on. And most of the time, they perform all of those operations at exactly the same time. So by choosing which one of the output or which output from which component becomes the actual output, you specify what is the operation that you want from the ALU. Okay. Now I can show you exactly what happens when I say I want a subtraction. And remember, this is subtracting 3 from 2. So what do you think should be the output? I don't want to do it just yet. Okay, I want you guys to figure it out first, and then we'll do it to verify that our understanding of how this works is correct. So what do you think happens when I click this 0 and turn it into a 1 to basically say I'm interested in the output of the subtractor, not the adder? 2 minus 3 is, go ahead.
It's all ones.
All ones. How about the carry?
1.
Yep. Okay. Because the carry is the borrow bit of a subtractor, so now we can see they all turn into ones, which makes perfect sense. Okay. Are there any questions about the ALU? Now, one thing you have to remember is the ALU has no ability to remember anything. It does not have registers. It does not have RAM. All it can do is to do a calculation and present the answer. As long as the input stays the same, the output would stay the same as well. But as soon as I change the input, the output will change. In other words, it has no capacity to remember a result. If I change this to a 1, you can see that the output is changed instantly. It doesn't have the ability to say, oh, save the previous answer. I'm just tweaking the input, but keep the output the same way. It doesn't have that ability. Okay, that is the function of what we call a register in general, is the ability to store something and just store it. So let the input change all it wants, but I'm not updating the stored bits, which is the output of a register. Any questions about the ALU? If there are no questions about the ALU, I'm going to do the next thing, to go to Project, Add Circuit, and turn this into an ALU. Go back to Main, and do zoom out first, because otherwise I can't really select everything. Go back to the selection tool. Take everything that we have here, and stash it into the ALU. So now I have a library part called an ALU, and from the outside, all we can see would be D in 0, D in 1, C in, D out, C out, operation select, and operation output enable. Those become the actual interface, but it will appear to be one single block, so we won't see the detail again when we look at, when we select this or use this as a component in main or other components. Any questions about this part? The questions? Okay. So now that this part is done, let's move on.
I have a question.
Go ahead.
Why do you leave so many spaces in the multiplexer instead of it's just so you can add stuff in later?
Yep.
Okay.
You can probably expect a homework assignment with adding maybe shifting and other things to it. It's not going to be difficult because all you have to do is to hook up the inputs, or at least one of the inputs. Some operations only require one single input to the component that is doing the calculation. Take the output of that component into the multiplexer, and that's it. Because you're using the multiplexer to choose which output is the one that you're interested in, even though all the calculations are done at the same time. Okay, so I'm just leaving that within ability to expand, but you can also see from the main component perspective. If I choose to put an ALU into the system, this is what it looks like. Okay, and I can expand the capability of the ALU without changing this interface. Okay, because the expansion has to do with adding more components inside the ALU to perform the calculations and specify a different bit pattern to choose the new components, but it has nothing to do with the outside interface of the ALU anymore. So this is a good way to encapsulate or hide details of the design. In a way, it is kind of like defining a class or a structure in C and C++, so that you're packaging things into one single thing, and for the most part, you don't need to know what is inside that thing. You just need to know what methods are provided to interface with that particular object. All right. Any questions? No questions? Let's take a look at registers, okay? Because I do want to show you, how registers are different from memory, even from the perspective of inside the processor. So this is the other, main component of a processor, of a modern computer, are the registers. So we'll do the same thing here. So we'll go to project, add a circuit, and this time I'll just call these, registers, and then we'll go ahead and define the registers. And some people might have noticed that under the category of memory, there is such a thing called register. So this is a good starting point, but it's not the only thing that we have to do here. So what we'll do is we'll have a single register here, and I'll call this register A. And then we'll duplicate this. Well, let's say we'll make a processor with only 4 registers. Okay, so we'll have 4 copies of these things, and change the names to A, B, C, and D. Okay. So now I have 4 registers, and it's a good time to take a look at each one and find out, okay, what can we do with a register, with a single register? So we just go ahead and hover our mouse pointer over one, and this is data value stored on clock trigger. In other words, this is the input into a register. Okay, if you want to update the value inside the register, you have to update the value at this port first. Okay, keep it stable. And then this one is called enable. When 0, clock triggers are ineffective. In other words, when this pin is a 0, you can specify any value at the port D, and it's not going to have any effect on the value of the register itself. Okay, it's kind of like a selection pin. Okay, am I being addressed? No, you're not being addressed. Ignore everything that you see on the data. This is enable. Value updates on trigger. Okay, so this one is the one that clocks and go. Okay, now go ahead and update. This is a reset pin. In other words, when you first start up a computer, you don't want your registers to have random values. Okay, especially a particular register is called a program counter. Okay, so for the most part, most of, if not all, of your registers should hook up to a line that is called a hardware reset. Okay, so when you first start up a computer, there's a special circuit inside your computer to guarantee the reset line is asserted or enabled for like some amount of milliseconds. So that gives all the different circuits enough time to internally reset the circuits so they start from a known state. Okay, and that's what this pin is for, is to make sure that when you first start up your processor, when you first power up anything, they start with a known state, and in this case, they start with 0. And Q is the output. That's actually that's the value of the register at its current state. So now we have a device. A register is a device where it can store and hold a value. Okay, whereas before we don't have any capability to do that, and now we have the ability to store and hold a value until such time you say, oh, I want it to change now. You, register A, I want you to update to this new value now. Are we doing okay so far with that concept, what a register is? In this case, register A can only hold and store 8 bits. Register B, the same way, C and D. So in this particular picture, we only have the storage of 4 bytes, okay? And each one is individually addressable. Are we still doing okay so far with the concept of a register?
What was the
Yes, sir.
second pin on there?
Say again?
What was the second pin?
The second pin, you mean the blue pin here?
Yeah, I get, yeah, that one.
It's called enable when 0 clock triggers are ineffective. In other words, when this pin is 0, when it's low, you can do whatever you want with D, and you can do whatever you want with clock. Nothing is going to change. It's going to ignore all of the other lines. It's basically the selection pin. It's basically saying, am I being addressed? Should I pay attention to the other pins? If it is a 0, it means no, ignore everything. You're not being addressed. If it is a 1, then you have to listen to both the input data pins and also the enable pin or the clock pin, because the clock pin says when to update, and the data pin is telling you what you should update to, the new value that is coming in. Is that okay?
That's like that LD then?
Say again?
Like the LD?
The LD. This particular pin is more like a cell, the select pin.
Okay.
Yep. All right. So given that we have 4 processors like this, we'll go ahead and figure out how to connect the 4 registers to the output, to the outside world. Okay, outside of the registers. Okay. Most of the time, you only need to access one of the 4 registers for one thing, and then you might need to do the same thing with another register. So what we'll do here is to use multiplexer again. And here's a multiplexer. And we'll change the select bit to 2 bits so that we can select one of 4 possible inputs, because we do have 4 registers here. I don't want to leave any space here, because with this, it's much more difficult to change from 4 registers to 8 registers than to say, oh, now we want to support bit shift operation. Okay, so with registers, once you decide on how many registers you want a particular architecture to have, it's very difficult to expand it in the future. And that's partially why the Intel processor, the i7 processor, with all the super duper features that it has, with all the performance enhancements since it was the 8086 processor, if you look at the number of registers, that really hasn't changed. It still has only like 8 general purpose registers and a few segment registers and stuff like that. The number of registers has not changed. Because in order to add additional registers, you will have to alter the very basic structure of the opcode, which makes the new architecture not binary backward compatible with the old architecture anymore. And that was the whole point of having the i7 processor still being able to run basically DOS in the old days, right? I mean, otherwise, why would you spend all the silicon on an i7 processor when you can spend the silicon to even enhance the processing power even more? There's a lot of circuitry inside the i7 processor or anything like that just to make it binary compatible all the way back to the 8086 processor. I think we have talked about this a little bit before. Have I talked about backward compatibility issues? Yes, kind of, no? Okay. All right, so here's the scenario. I'm digressing a little bit from this picture here. So here's the scenario. Let me bring you to a web page here. Let's go to the Debian web page. And what I want to do is just to give you an idea of how many architectures are supported by the Debian distribution. So let's see, where should I find it? Oh, I know. I just have to look up one package. So I look up Linux image. I go to Debian packages. It's quicker to go this route. Okay. Okay, so these are the images supported by. Oh, okay, there are too many. There we go. So we'll look for a fairly modern image. You only have to. Oh, I see. Because I chose stable. Let's choose unstable. Search again. Amiga. I did not know that Linux is available for the Amiga. Okay, they changed the name to kernel image. Okay, that's fine. Actually, any package here will reflect architectures all. Yeah, that's not what I want. Okay, this actually gives you an idea of what kind of architecture, Linux is supporting. So let me see if I can. I just need to find one place where it's easy to find out what architecture is supported. Okay, I know.
Aren't they listed across the top there?
Oh, limits to architecture. That's it. Thank you. In plain sight, right? Okay, so if you look at limited to architecture, let me just highlight that line here. These are the code names of all the architectures supported by Linux, or all the architecture that can run Linux. In particular, in this case, a Debian distribution, which is possibly a subset of all the possible architectures, because they probably just pick the ones that are quote unquote more common and more popular. There might be some additional architectures or processors that is not listed here because it's kind of like a one-up kind of thing. But if you look at this list here, even though there are entire families of stuff here that are related, like all the ARMs are kind of related, i386 and IA64, they're kind of related. We have the Spark family here, Spark and Spark 64, they're related. SH4 is a Hitachi processor, which is very seldom used in actual computers. S390 and S390X, those are IBM mainframe architectures. PPC, PowerPC 64, and Power 64 EL, those are related to the PowerPC architecture. So this bunch are kind of related. It's one family, but they have specializations as well. We have the MIPS processor, which is a research type of architecture originating from UC Berkeley. And then we have the Motorola M64K, or the 68,000 line of processors. So in other words, it is supported by, it has a port to many different architectures. And this is not an exhaustive list of what Linux can run on either. I mean, this is just a selection that Debian has decided, okay, we're not going to support the other architectures because it's too much work and we don't want to deal with it. Okay? How many architectures can Windows run on? You can count 32-bit as one and 64-bit as another one. So there are two, and then we have the ARM architecture because on mobile devices, Windows has a special there's a special version of Windows that run on mobile devices. So there are three. Okay, let's call it three architectures. And I think Microsoft used to support the AMD 64-bit architecture, or the Intel, the old Intel 64-bit architecture. I don't know whether they still support it or not. So maybe 4 or 5 architectures all together. Why do you think it is a much smaller selection compared to Linux?
It's cheaper to make software.
It's not as much work.
Not a whole lot of work. And also that's the driving force of making Intel and AMD processors backward compatible. What do you think happens when Intel says one day and say, well, we are wasting all this silicon in the i7 processor for stuff that is not needed anymore. So starting with the NIX architecture, it will have no backward compatibility, but for the same die size, the performance will be doubled. I think people like performance, so we want to double the performance, but it won't have backward binary compatibility anymore. What is that implying? What is the lack of binary compatibility?
You have to start over.
That means exactly. That means your current Windows would not run on the new architecture anymore. Okay, how much work is involved in order to make an operating system? How much work is involved to port an operating system to a new architecture? Well, with Linux, it's not really a lot. Okay, there are architectures out there when the processor is still being designed using not logic sim but a much more professional tool. When the architecture is designed but before it is fabricated in silicon, it's still in simulation, the operating system in Linux is ready already. In other words, before you take delivery of the actual hardware processor in silicon, and the processor is still being run in a simulator, people are done with porting Linux to that new architecture. That really kind of tells you how much work is involved. I mean, I'm not saying it is trivial, but at the same time, it's not as much work as creating a new hardware architecture either. Okay, are you guys kind of following what I'm saying here? Okay, so if that really is not that much work to port to a new architecture, why do you think some companies still want to hang on to the x86 instruction set?
It's where all their money's invested.
Say again?
It's where all their money is invested in.
Say again?
It's where all their money is invested in already.
Well, I'm guessing they did not write the operating system in a very portable way, so it would cost them more manpower in order to port the operating system to a different architecture. But what we are paying, as the price of, staying, with the x86 architecture, is the power to processing power ratio, the energy to processing power ratio, is not really so good. I mean, the i7 processor, by any means, by any standard, is a superb design. Okay, in terms of power efficiency. But if it doesn't have to maintain the backward compatibility, it would have been an even better processor, for sure. Okay. Yep, go ahead.
What's the big difference between the x86 and the ARM processors and cell phones?
Oh, they're completely different. The number of the instruction set is completely different. Even the basic idea is different. The ARM architecture is a fairly standard RISC architecture, reduced instruction set computer architecture, which means the number of instructions, possible instructions, is fairly limited. It's still probably at least 100 of them, but it's not nearly like 500 or 600 like the Intel architecture. And the number of registers are different. Our RISC architectures tend to have more registers, general purpose registers, where you can say, oh, any one of these 32 registers can feed into this adder here. Any one of these 32 registers can do this. Whereas with an Intel architecture, there are special purpose registers. For certain instructions, for certain operations, you can only use a particular register for that purpose. And that came from the old days of the x86 architecture, and they have to maintain the backward compatibility. So there's no way to change it, even though now we have the ability to do it, but because we want to maintain the software backward compatibility, we still cannot make changes inside the processor to make that happen. So getting back to what we were doing, once you fix the number of registers, it's very difficult to change it in the future without breaking backward code compatibility. Okay. So let's say we only want to have 4 registers in this particular architecture. So what we do is we say, okay, let's go ahead and feed all of these into the multiplexer here. Okay, so we have, all right, fix the multiplexer first, and we'll have 8 data bits per channel. And I have done this enough times to know how to draw it so that it doesn't have too many overlapping lines. Okay, so we have now the output of the 4 registers going into the multiplexer, and the output becomes the output of this entire module. And we'll go to the pins again. Basically, a pin, if you look at a pin in wiring, it's kind of like either the parameter of a subroutine or the return value of a subroutine. This is the interface into this particular module, input and output. So in this case, we have, this is an output. The number of bits is 8. And then we'll change the label to register output 0. And we'll have another one as output 1. And we'll make it face south. So duplicate, make a second one, deal with the second one later. Okay. So now we have register output 0, and we can select any one of the 4 registers to become the output of this entire module. Okay. But if you remember, with an ALU, we can potentially have what? 2 inputs, right? So what if I want to perform an addition, and one input comes from one register, and the other input comes from another register? Well, you can do it in 2 clock cycles, where in the first attempt you get from the first register, and then in the second attempt you go get another value from another register. But you can also do it this way and have 2 multiplexers instead of 1. So now we can have another multiplexer here, and say, okay, the second multiplexer is going to have basically exactly the same input here, but the output goes to the second 8-bit pin. So now we can have 2 output pins and 2 multiplexers. So with the 2 multiplexers, now we have, we need to specify, there are 4 total bits to specify, okay, what is the output of the first multiplexer, and what is the input of the first multiplexer, and what is the input of the second multiplexer. So those would have to be going to the outside world as well, because somebody else has to make that choice. So now we bring these lines down here and specify a pin facing north. 2 data bits will be enough in this case. And we'll call this one register select 0. And just put it here. And duplicate this. Oh, I hooked it up to the wrong line. Okay, there we go. And then we duplicate this, change the name to 1. I forgot to do the same thing here, so maybe change that first. There we go. Could have drawn this in a different way to avoid the crossover.
Just drag the pin over and it should drag the wire with it.
There we go. Yeah, but it will do it in a weird way. Oh, there we go. Nice. Thank you. There we go. Nope. There we go. All right. So we still have a few lines that we need to connect, as far as the output is concerned, because we have the blue pin coming from the multiplexer that is not connected. In other words, am I driving this output here? Am I driving the other output here? We'll just go ahead and have an external pin to decide that, so that we don't have to decide from inside this module. So we'll have this is still an input pin. Data bit width is only 1, and we'll have register 0, label 0. What about the input? What if I want to change the value of one register? Now, as far as the output is concerned, I need to be able to select two outputs at the same time. That has to do with the ALU. Because the ALU can potentially take the output of two different registers in order to compute the sum or the difference. So that's why we have two outputs here. But the input only needs to be one, because we only need to update one register at a time, because the output of the ALU only has one single output, one single 8-bit channel as the output. So as far as this module is concerned, as far as the input is concerned, we only have to select one of 8 possible inputs. Excuse me, and we only have to select one of the 4 for the update operation. So in order to select one of the 4 update operation, we don't need to use a mux anymore, because we have the ability to use this pin here. We can use the enable to say, oh, okay, you are the one that I want to update. Even though the input data is presented to all the registers, only the one that is being addressed would actually pay attention to it. The rest would just kind of ignore what is going on, with those pins. So that's why we don't need a mux in this case. We just need what we call a I keep forgetting the name of those things, decoder to do it. So decoder is all that we need in this case. So we first define the 8-bit pin, and we'll call this register input. It's going to be input. The number of data bits is going to be 8. No need to specify tri-state. And that becomes the input into this entire module. Component cannot have negative coordinate. Great. Okay, now I have to move things over a little bit. Like that. Okay. And make it face south. And there's no problem with connecting this pin to all of the data input pins of all the registers, because unless a particular register is enabled or selected, they're ignoring everything. So that's good. That's okay. We need 2 bits in order to do a selection of which one am I updating, if I'm updating anything. So that means I need to look to pins again, and this time I will have 2 bits, and it is input register selection, and make it face south. So, well, I'll put it over here, make it face the other way, face east. There we go. And then this will go to what we call a decoder. So a decoder basically takes, in this case, it will take 2 bits in order to select one of the 4 possible outputs. We looked at this already when we looked at memory modules, remember? The most significant 2 bits of your homework, select one of 4 banks of memory, of RAM modules. So in this case, it's kind of like the same thing, except we have to select one of the 4 registers in this case. So we hook up the input pin into the input pin of the decoder, and then the decoder, from the decoder there should be 4 outputs. Let me change that to have 2 input pins, and automatically it switches to 4 possible output. No tri-state. The disable output is floating, or we can just make it 0. It's just kind of more handy to make it 0, so that will automatically disable a register. And it's complaining because oh, okay, output to the wrong line. Yep.
It'll automatically disable what, sir? I didn't hear you. You said it'll automatically disable
The registers. Okay, let me hook this up first, and then I'll explain that. This is enable, this is select. Okay, there we go. So this has to go here. Okay. This pin here is an enable pin. So if the enable pin is 0, then it will just ignore whatever is the input. None of the 4 lines would get a 1. Okay. if I use the floating feature, that means the output, instead of forcing each output to a 0 when none is selected, the output would be floating. Now floating is good sometimes and not so good other times. If you have, okay, let me draw a picture here. Okay, so if you have two lines connecting into the same net here, so let's say this is the output, these two are potential inputs. Okay, if you can make the circuitry so that these two lines coming in can either both be floating or only have up to one that is driving the signal, that's good. Okay, so you're saving yourself from having to use a multiplexer to combine the input into the output, because if only up to one can be driving, then you won't end up with a fight. On the other hand, if both of these can be driving, then you can potentially have a problem, because you can have one driving high and one driving low, and then all the current will be going in this direction, and you end up with a bus fight. So these components will heat up really, really badly, because they're not supposed to handle that much current. But in this situation, when I hook up the decoder output to each one of the registers, each one only has one going to one particular register, so I don't end up with the same problem that I'm trying to avoid using a floating line. And the thing about the floating line is, if you use a float line, the problem is it becomes an antenna. Your trace becomes an antenna. So whether the voltage on that trace is high or low depends on a lot of things, because no one is driving it, right? So it becomes a floating line. So it depends. You can induce current in it, and so there's a voltage on it, and that's not good. So you don't want to use floating in that type of a situation. So now we can specify this enable to go here, and this one to go here, this one to go here, and the last one to go here. Okay, we're almost done. We only got 2 more pins of each register to connect to. The EN pin is already done. The one with the little notch is called the clock pin. That one is basically saying, okay, I know that I am addressed. I can see the data line, or the D pin is presenting, some data. When am I supposed to update my value? Okay, that's what the clock line is. The little notch line here. Okay, let me point it out here. This is a clock line, and it updates on trigger. It doesn't really say whether it's a rising edge or falling edge. The memory modules that we're dealing with will update on the rising edge. So I'm guessing that this is also a rising edge type of clock signal. Not sure yet. We can try it out later. But basically that's a signal, and say, okay, when you see a low 0 to 1 transition, update. Take whatever is in the input pin, which is the D port of a register, and update your internal state to that value. Okay, so is that okay so far? How a register works? Okay. So that one has to be brought outside as well. So we now need to go pick up another pin, and we'll call that register right line. It is an input pin. We only need 1 bit for that. We don't need tri-state for that. And that's okay. Make it face north, just so that it's easier to connect to the pins that we want to connect to. There we go. And this one we can connect it to all of the pins at the same time, because it has to do with the decoder is only selecting up to 1 register. So if a register is not selected, it will just ignore the clock line also. It won't get updated. It won't update its internal value regardless. And now we only have 1 line left, which is the reset line. In other words, when the processor is resetting, we want all the registers to start with a value of 0. Okay. And I'm running out of space on this side to, I suppose I can use this part here. There we go. Bring it all the way down here. Just duplicate this one because it has the right orientation already. So we'll call this one just the reset line. So that when the reset line is a 1, it will 0 all the registers. We're starting from scratch. Okay. And it has the same connection from all the registers. They can all go to the same reset line. So, all right. So now we have the register submodule, basically all done. Now is a good time to test it. So before we incorporate a submodule into the main design, it's always a good thing to test it first. So let's figure out, what we need to do in order to update oh, I'm missing one. I'm missing this one here. That's the enable of a register. So we'll bring this out also to a particular pin. We'll call that register write enable. In order to say, yes, we want to perform it right, I'll rename the other one as register write clock because it's the rising edge that is important here. This one has to be on, and this one has to experience a rising edge in order for a register to get updated. All right, so we are all done, with all the connections. Now it's a good time to test it. So let's go ahead and zoom out just a little bit. And now we can see the entire thing, and we'll go ahead and test it. So let's see what we have to do in order to update. Let's say I want to update register C to a value of 10100101, okay, which is A5 in hexadecimal. Okay, so what do we need to do to update register C to 10100101?
Change the register selects.
Okay, so we'll change register in first, okay, because we're presenting the data. Okay, now some of these orders can be switched, okay, so we specify 10100101, okay, and then we have to select that particular register. Register C is 0, 1, 2, okay, so what is 2 in binary? 1, 0, so register in select will now be 1, 0 in order to select that one. Okay, but you can see that without register write enable, none of the register is selected to take on a new value, which is perfect. This is what I want, okay? Because I don't want them to pay any attention until I say, okay, you, register C, go ahead and pay attention now. And that's what we're going to do now, is to say, okay, whichever register is selected, I want you to pay attention because we have a pending write operation to you. Okay, you can see the green line is now, the lime green, the light green line is now going to register C, and only register C is selected. Okay, so that any further operation will only be performed to register C. Even though registers A, B, and D are still connected to the D line, to the register in line, they're going to ignore everything because they're not selected, they're not addressed. All right, so what is left to do now is to use a clock line here, register write clock, and I think a rising edge is going to update it. It doesn't save, so it's not documented. So we'll go ahead and give it a rising edge, and you can see register C is now updated to A5, and A5 is the hexadecimal representation of 10100101. Okay, so typically with a clock line, you don't want it to stay in one state, so we'll turn it back into 0. And since we're all done now, we'll also turn the write enable line back to 0, and now register C is updated. Are we doing okay so far? Okay, so now hypothetically speaking, let's just say that we want the value of register A to be presented to register out 0 because we want to perform some calculations. What do we need to do in that case?
We need to change register select 0 to represent the 0
Okay, so we need it to be 0, 0 because we are selecting register A.
That's right, sir.
Did I say register A or register?
I think you said, I heard C, but I could be wrong.
Register C? Okay, well, we can do C. Okay, register C is 1, 0, so yeah, I have it selected now, and you can see that register output is automatically updated already, which is not what we should do.
Tri-state.
Yeah, because I selected tri-state enable, so let's say no, and yep. Okay, there we go. So without this, it's not going to drive the output, but with this selected, it should drive the, oh, okay, wrong pin. It will drive the output. So this module now has all the pins as the interface to a bank of 4 registers. And it is not memory. Remember, registers are not a memory component. They are basically internal to the processor, whereas memory usually is outside of the processor. Okay? And usually have a very small number of registers as opposed to a lot of memory. Just from this picture here, can anyone kind of tell me why you can only have a small number of registers instead of like kilobytes or megabytes of these things?
Too many wires.
Too many wires, exactly. Just imagine this picture. If I have 1,000 registers, okay, what would this picture look like?
1,000 times bigger.
Okay, and the worst part is not even visible, okay? Because if I have 1,000 of these registers, most of these lines are multi-tap, okay? In other words, the same line goes to every single one, which is not a big problem. But if you look at the internal of a multiplexer, it's complex, okay? It is very silicon intensive because what it does is a traffic controller. So just imagine you have 8 bits as the input of one single port of a multiplexer. With 1,024 registers, we'll have 1,024 times 8 as the input into the multiplexer. And that's just the input. But internal to the multiplexer, it needs the circuitry to basically say, of the 1,024 possible input, I want to route the 8 bits of this particular input to the 8-bit output of the multiplexer. That is silicon intensive, okay? And that's a main reason why we cannot have that many registers. It has to do with the limitation of the multiplexer and how to cross circuit with all of these things. And remember, we have 2 multiplexers too. Okay, with 1,024 registers, you have to do the same thing to the other multiplexer, which becomes a problem when it comes to actually implementing the design on silicon. A lot of things that is easy to specify on a picture like this, which is what we call a schematic, sometimes is difficult to do on silicon. It is not uncommon that people can specify a design on paper using a picture or a schematic like this that is not possible to implement on silicon. Well, how can it be so difficult on silicon? Well, with a picture like this, you can see the connections are all logical, okay? Is this line connected to that? Is this pin connecting to that pin? Yes, okay? And we can cross over all we want, right? Because the crossover is not an issue. If you do not see let me just zoom in here to make my point. If you don't see a dot here, that means it is not connecting. It is just crossing over, it's flying over. If you see a dot, that means it is actually making a connection. And you can cross over many connections here on a schematic capture without causing an issue. But what about on an actual circuit?
You have so many
It's
layers.
two-dimensional. Sorry, go ahead.
You only have so many layers that you can do.
Exactly. Now that's only with a circuit board. Now when you're laying down silicon, you have even more limitations. Because silicon is based on etching, and that process is only deletive, it is not additive. In other words, with silicon, now this is something that I'm not an expert in, but I know enough to be dangerous. So the way a wafer works is it has multiple layers like this, okay, with different types of material. So they use a process called doping in order to create these multiple layers. The primary layers will be like N layer and P layer. Okay? They're basically doped with different types of quote-unquote impurity into silicon. But the process to make a circuit board work is, they use a deletive process. In other words, you can basically end up with a cross section that looks kind of like this. By edging out, by deleting, material on each layer, that's how you make a wafer work. Okay? But this gives you a lot of limitations because once again, it's a two-dimensional thing, and you cannot really cross over things very easily. On a circuit board, if you run out of the routing resources, there are other ways to make a connection. It's called a jumper wire. Okay, nobody knows what a jumper wire is?
Yeah.
Okay, so on the regular circuit board, okay, so what you do is if you want to be cheap and use a single layer circuit board, and then you say, oh my goodness, I cannot, there's no way for me to bring a connection here all the way across into here on the printed circuit board itself. It's no big deal. You just solder a wire and solder it on the other side. Problem solved. No problem, right? I mean, that's easy. Can't do that here. Okay? If you want to do something like that here, that means, on the circuit, on the chip design, on the specification, you have to specify this particular pin must connect to that other pin over there. Okay? And people don't do that, okay? For two reasons. One, once you have external wire, it's longer. Okay, it's longer than the internal connection, and the longer wire means a better antenna. In some situations, you want to have a better antenna, but not when you're designing circuits. Okay, because it will pick up noise, or it will induce noise. It becomes a noisy component. Okay, so you don't want to do that, and that's why when you design a circuit on a chip, you have extra constraints that you don't have when you're actually designing a circuit board. A circuit board has multiple layers. If you look up the specification of your typical motherboard, they are typically, 8, 9 layers these days? Okay, what does that mean? That means, you have, that's 4, 5, 6, 7, 8, 9. Okay, this is a 9-layer board. Each blue line is representing a copper layer, okay? A copper layer simply means, it is a piece of copper, and you can etch it and delete, and have, traces, done to it. But a 9-layer board has a lot of flexibility compared to silicon over there, because by drilling holes and inserting what we call vias, VIA vias, you can actually say, oh, I want this signal here to go all the way down here. No problem. Drill, 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 drill. Put in a via, which is a conductor. Now you have a connection to go all the way from here to here. Okay, and that's why having a 9-layer board is sometimes necessary in order to design modern computers, because there's so many connections coming out of your memory modules, going all across, going to all over the places. So you need that many routing layers in order to make it work. Not here. Can't do it over here. Okay, and that's why and that brings us back to this circuit here. Even though on paper, in terms of a schematic, a multiplexer is just a simple thing, in terms of implementation, because of these problems, it is not a simple device to design. It takes up a lot of silicon to make it happen. Okay, one of the things that people run out of, when they design something complicated on paper without consideration of what happens on silicon, is they run out of routing resources. That's the first resource to run out when they design something that is too difficult to implement. And there are, I know we are running out of time, but to go from this onto silicon, the tool is called a compiler. Okay, it's a hardware compiler. It takes the logical design, how one component connects to another component in terms of gates or higher level components like this, and it compiles to what we call the silicon design. And at least back in 2000 or so, it's not a science. It's more like witchcraft. Those tools comes with like 20 gazillion little check marks and say, you want to try this trick here? You want to try this trick here? And sometimes combinations of tricks will work for a certain design, and then the next version of the software, it doesn't work anymore. It's really touchy. It's not an exact science. So that's kind of the limitation of what people run into when they design processors and hardware stuff like that. So we're running out of time today. I'm going to save this at least on my own computer so that we can use it again later on to complete a more complete design of the processor. But we're doing components right now. We're simply doing components at this point. I'm not sure whether you guys get the idea or not, but I'm really enjoying this. This is like Legos for me all over again.
I have a question from
Yes.
ALU. We supply 2 from 3.
Yep. No, you're subtracting 2. Yeah, you're subtracting 2 from 3 and then you're subtracting 1. That's
Yeah, but in our case.
no, that's subtracting 3 from 2.
I see.
Yeah, because with the subtractor component, you're subtracting the bottom value from the top value.
I see.
Yep.
That's fine. Thank
Yep.
you.
Mhm.
Yeah.